Okay, let's get started. Yesterday, where we left off was on this slide. We talked about how you can join the same table in twice by using the from clause. And then we also showed you the indirect join, where at the bottom, we call it daisy chaining, where you're not joining on the base table, you're actually joining on an intermediate table. So now we're going to talk about the anatomy of SQL in LookML. So let's revisit how Looker generates SQL. A typical select statement grabs one or more columns from a table, possibly with a join or two, on some columns where some filter condition is met. When you've constructed an Explorer, Looker populates the end user's chosen dimensions and measures as the columns to select. The from clause uses the base view, and any required joins are added with the provided SQL on logic. And if the user adds a filter on a dimension, such as a date filter or a country filter, this becomes the where clause. Here is an example SQL query you might have needed to write by hand pre-Looker. We are selecting 4 columns from flights with left joins to aircraft and airports. With this Explorer, Looker can write that SQL query for us automatically. The 4 columns being selected would be 3 dimensions and 1 measure residing within 3 views. The type and SQLon parameters in the aircraft and aircraft origin joins determine how these joins should work. We have some helpful parameters to clean up Explorers, similar to the ones that we used earlier to clean up views within an Explorer. First is label. Label changes the name of the Explorer in the front end. Our Explore order items might confuse business users, so we could add a label to make it appear as something more friendly. So let me show you that. So with this label in Explorers label, what it changes is what it says right here. So items and orders and items explore. So if I, let's say add some text, refresh. So the label parameter displays how the Explorer is going to, be viewed in the Explore dropdown. Description adds a tooltip that displays upon hover, same as when you use it on a dimension or measure. And same as with dimension or measure, any text string in the description would cause the Explorer to appear in the search results if someone tried to find and explore it in the drop-down menu. So let me show you what description does. So in this Explorer, I have a description called Investigate Orders and Explore, or Orders and Items. Now, when I go into the Explore dropdown and I see Orders and Items Explore, this information key is what this description does. You see how it says Investigate Orders and Items? That is coming from this description key right here. So that's what the description parameter does. View label changes the display of the view name. Remember, usually the base view name is the Explore name. If you use a label to change the Explore name for user friendliness, you might also want a view label to change the name of that same view within the field picker. Additionally, you can use view label to merge multiple views by giving them the same name. If you have two views that technically map to different database tables, but are conceptually close enough that it might make more sense for a business user to perceive them as just one view, you could assign the same view label to both. So let me show you what view label does. So view label right here, orders and items. What that does is change the base view's name to orders and items. So let's add some text to it just so you see how it changes. So now I got those $sign in front of it. Now the other thing that was talked about was, in our situation, what if we want to group inventory items and products together in one view dropdown? We can do that by changing the view label, the two joins. So these two views, we're adding the same view label, and look what happens. So right now we have a products dropdown and we have an inventory items dropdown. And now when I hit this refresh, now we see a dropdown that says products and inventory items. So now all the fields are grouped into here, both from those two views. Now this certainly doesn't make sense for our example, so I will highlight those back out. But I just wanted to show how that can be useful. Group labels let us define a custom header for one or more explorers in the drop-down menu. Otherwise, by default, all the explorers will be under a header that comes from the model name. If one model has many explorers in it, it can be beneficial for the end user experience to break them up via various group labels. Let me show you group labels. So there's the group label parameter. I'm drawing a blank on where this actually is being affected. My apologies. Shit, we'll skip it.
I think group label is on the Explorer within the main view drop down, like orders and items. Within that, you can group things.
Oh, exactly. Yeah, you see. Thank you, Dan. Appreciate it. So what we changed is Data Analyst Bootcamp with 3 exclamations. So now there's a group label right here. It shows up in the Explorer dropdown, and that's what we just changed, the group of the explorers that come from it. Thanks, Dan. I really appreciate you helping me out there.
Sure, and actually, I'm glad you thought of that, because I was thinking of the words I was saying. I was thinking of even a different thing. It's hard to remember which LookML parameter to use to change which thing in the user interface. You have to, I always have to refer to the documentation to keep straight, like how to change which label. So anyway, it's hard to remember.
I agree. It gets confusing. The last one that we're going to talk about is the field parameter, which lets us limit the field presented in an Explorer or view. It is similar to hiding fields via the hidden parameter, except using fields will tell Looker to treat those fields as if they don't exist at all within a particular Explorer, so attempting to use them would result in errors. Meanwhile, hidden fields would actually still work. They just wouldn't be visible in the field picker. Both fields and hidden would be used to ensure only the relevant, meaningful fields for analytics are displayed, and business users don't feel overwhelmed. So where is a fields parameter? Give me 1 second. Here we go. So here's my example of using the fields parameter. Basically what I'm doing is I'm joining in the users table, but as far as the fields that you're allowed to pick from, I'm only saying you can only pick from these 4 fields. So right now, without that functionality turned on, we're getting all the fields coming from the user's view. But if I only want the user to select from the ones that I define, now when I go into the Explorer, if I go into users, it's only showing me what I said in the fields parameter. So this is helpful to limit the fields that the user can see. But you can also use the hidden parameter, which I use very often as well, to do functionally the same thing. All right, now we will get to develop our own Explorer. So a product analyst wants to know who signed up for our website but still hasn't ordered anything. What do we know about them, and how can we entice them to buy stuff? So what this is calling for is for us to build a new Explorer, but this time, instead of the order items being the base value, as you see right here, we're going to make users the base value. And then we're left joining the order items table and the inventory items table. Let me give you this code, and you guys can drop it into your model file. So when you add it to when we as in building this Explorer, the way to get to the Explorer would be go into the Explorer, and now instead of just one Explorer, we have 2 Explorers that we can choose in the drop down. The one that we just created is called Users, and it's a lot smaller. Notice that we only joined in the order items and the inventory items table, and that's what we see: inventory items, users, order items. So only 3 tables. The joins are the type of join is the same. It's a left outer, but this time it's a one to many from users to order items, because there are many user IDs and only one user ID per row. So in these ones it was all many to one, and that's the most common that you're going to see is left outer and many to one joins, because that's for a star schema. This one is one to many, and the inventory items is a many to one. And this is an indirect join, since we're joining on not on the base table, but a secondary table. Let me just show you how this works.
Hey Danny, this is Carrie. Sorry, I might be behind. You just took what you sent us there and you pasted it in the dot model file
Correct. Yep, at the very bottom.
at the very bottom. That's my problem. Thanks.
Yep. So I just made a line chart, total sales by delivery week. Just want to call out what's going on in the SQL. So because the users table is the base view, it's what's defined first in the Explorer. That means it's always going to be in the from clause. It's always the first table that gets joined in. In this example, we're not even using anything that comes from the users table. We're using two fields that come from the order items table. But because this is the base view, it's always going to be a part of the join. Now we are left joining in the orders item table, and that's going to give us the two fields that we're asking for. So yeah, this is cool. Through the what we define in the Explorers, it knows what the exact join is going to be. It really handles the SQL for us. All right, moving on. Symmetric aggregation is a special Looker feature that ensures accurate aggregation of data for counts, sums, and averages. It addresses a common problem in data and analytics called the fan-out problem. Imagine you have two tables, customers and orders. The customer table stores customer data such as customer ID, first name, last name, and the number of visits they have made to our e-commerce platform. The order table stores order data such as order ID, the amount of the order, and the ID of the customer who placed it. The relationship between the tables is one to many because a customer can make multiple orders, but each order can only be made by a single customer. When considering these tables individually, the count and sum operators produce accurate results. There are 3 total customers, 3 orders, 8 total visits, 4 orders, and $250 in total order spend. We need to join these two tables in an Explorer so the business users can analyze data across them both. It is pretty clear that customer ID should be the join key. However, when we join them together on customer ID, given the one-to-many relationship, we actually produce what is called a fan-out. This table illustrates the result of the one-to-many join, which fans out the customer table. It introduces a duplicate row for customer ID 1 because Amelia made more than one order. When performing aggregations on the customer side of the table, we now get incorrect results. The sum of visits amounts to 10, whereas we as human beings looking at this table are capable of realizing that one of those twos is a duplicate, and the true answer is 8. Likewise, a count star of customers yields 4 rows, which we can tell with our own eyes it should be 3. On the order side of the table, the aggregations return the same results as they would if orders were a standalone table, as no fan-out occurs there, the many side of the join. I want to emphasize that this is not a new problem caused by Looker. It is an old database problem. I used to work at a company that offered invoice and payment reports to our customers. A customer could pay multiple invoices with one payment or split one invoice into multiple payments. Reports that included many invoice and payment amounts together always inflated the totals because some invoices or payments were being counted multiple times. We had to tell our customers simply to ignore the totals at the bottom of the reports. So symmetric aggregation is really cool because it finally solves this problem that has been around as long as databases have been doing joins. It is not a feature that we as LookML developers need to be conscious of activating. Instead, it is something that occurs on its own when needed as long as two conditions are met. First, every view file must have a primary key defined if you plan to join it to an Explorer. To make life easier for yourself, you should simply strive to define a primary key in every view, period. Second, the relationship parameter needs to be specified correctly for every Explore join. An easy way to test if a primary key is unique or not is to compare a count of the fields you believe to be a primary key against the count star on the table. If the two tables return the same number, you have your primary key. If not, you can create a dimension that concatenates all the columns necessary to make each row unique. You cannot assign a primary key parameter to more than one dimension in a view. For join relationships, there are 4 possible values: 1-to-1, 1-to-many, many-to-one, and many-to-many. The left side of the relationship value refers to the view that appears first in the Explorer in an earlier line of code. The right side is the view being joined in later, i.e., farther down the code file. In this example, 1 refers to customers and many refers to orders. The order in which fields appear in the SQL on parameter does not matter. Aside from ensuring that your substitution operators point to real dimensions or measure names, Looker and the LookML validator does not actually check anything in the SQL parameter or any parameter that starts with SQL. If it helps you figure out what the correct relationship is supposed to be, you can construct a sentence for each possibility and think about whether it makes sense. Personally, I find it easier to think about the join keys. Is customer ID the primary key, or are all the values unique in this view? What about the other view? Is it possible the same value could appear multiple times there? What would happen if we specified the wrong relationship between customers and orders, say 1-to-1 instead of 1-to-many? The data on the customer side would fan out. Remember, we only had 3 customers. Their combined visits totaled 8. But here in the Explore result, we see 4 customers with a total of 10 visits. Amelia is counted twice, along with her 2 visits. What would happen if we specified the right relationship between customers and orders? 1-to-many. Looker would automatically apply symmetric aggregations, resulting in the correct outputs of 3 customers and 8 total visits. So let's show how this, how important this relationship key is. Let me pick something that's simple. That should be good. So here are the totals. These are the right totals for total sales by the days since sign up tier. But what if I make this relationship wrong? I change it to 1-to-1. Now when I refresh this, the values are going to be different and wrong. I wish I wasn't able to tell whether it changed, but the relationship is now defined wrong, so the join isn't right. How does this all work? Counts are pretty straightforward. You might have already been wondering why Looker wouldn't do a count distinct. Indeed, we have finally come full circle with a statement I dropped a while ago. Measures of type count do the equivalent of a count star, which counts all the rows, but in some cases, it counts the primary key. These some cases are when symmetric aggregations are at play. Since this query executes a one-to-many join, Looker realizes it needs to count distinct customer IDs rather than a blanket count star. The latter would likely factor in many duplicate customer IDs from the orders side. Sums and averages are a bit more complex. People are often alarmed when they click on the SQL button in the Explorer and behold a query like this. For assurance, you can look for instances of MD5, which is a hashing function, and then you know this is just Looker doing symmetric aggregation. Don't worry, you don't need to learn when and why to use MD5 to be a successful LookML developer. What Looker is basically doing in this example is generating a unique numeric amount for each primary key value. So the two rows for Amelia would both get assigned a random value instance. And then to calculate the true total visits, Looker actually does a weighted average where it multiplies or adds just a big random number to the value, and then subtracts it back out, and it gets you to the correct number using symmetric aggregation rather than the fan out solution. It's very complicated. You don't really need to fully understand it, but this is a really cool feature because you're going to reach the fan out problem in many scenarios, and it always inflates the value of metrics, but you don't have to worry about that just as long as you define primary keys and get the relationship correctly defined. Looker's going to do some special arithmetic to make sure that nothing gets double counted. So far, we have created dimensions and measures, explored and joined views, and learned about the importance of having a primary key assigned to each view and defining the correct join relationships. A useful way to take your explorers to the next level is to filter them. To filter an explorer means to apply a default where or having clause to every SQL query that gets generated in that explorer. There are three principal ways to filter an explorer. There's really four, but we can think of two as the same thing: the SQL always where and SQL always having. There's also always filter and conditionally filter. We will discuss common use cases for each of these. You would want to use SQL always where or SQL always having when you have some immutable logic. In other words, there are certain rows of data you want to exclude from the Explorer results, and you never, ever want to let business users change that. Business users will not even know that anything is being filtered. There will be no indication of it in the user interface unless someone happens to have permission to look at the generated SQL, and then they'll see it in a where or having clause. A popular use case for SQL always where is test data. Say our software engineers also create test users who place test orders, and those test users always have the word test in their name. We definitely always want to omit the test users and their orders from the Explore queries, because those test users live in random places like Antarctica and place multi-million-dollar orders. They would dangerously skew our customer and financial reports. Hence, we want to add a SQL always where clause that makes sure that there's no test data in our data. As for SQL always having, we might have survey data that we want to analyze in Looker. For official surveys, responses to a question cannot be published until a minimum number of responses have been received to protect participant anonymity. So we might set a SQL always having clause on the Explorer that checks to make sure that the count of responses is greater than 5. I once worked with a customer who wanted to analyze success rates of their email marketing campaigns. What percentage of their customer base opened the emails? What percentage of those people then clicked on the ads in the emails? What percent ended up purchasing something through the ad? I developed an Explorer that initially showed lots of 100% rates, which was thrilling. But we dug deeper and noticed that these were all tiny campaigns targeting about 25 people. My customer did not care about these small campaigns, so we added a SQL always having clause to make sure that the count of emails was greater than 1,000, so that this would only consider major campaigns. Remember, because the Explorer is the foundation for all content in Looker, Explorer filters always trickle down to looks and dashboards, and by extension, any schedule and embeds using that content. So let's show you what SQL always where and SQL always having does in Looker. So in our orders items Explorer, let's add a SQL always where clause to only look at users from my home state, Michigan. I can paste it in the dropdown if you guys care to do it yourself. So in adding the SQL always where clause, state equals Michigan, you don't see anything that indicates that this is only Michigan. And that's by purpose. This is a scenario where you don't let the user see what's being filtered. The only way to know that the filter is being used. Oh, I'm on the wrong Explorer. So we're just looking at total sales by delivery week. We go into the SQL, look at where that SQL always where clause gets applied. It gets applied as a where statement. So this is only sales for Michigan. Now a SQL always having is pretty much the same as a where clause, but it's on a metric, and it's post aggregation, comparing the value of the metric. So in this scenario, we only want to see where total sales is greater than 1,000. So let me show you how that works. So in the Explorer, you see a having clause now that says we're only going to be looking at data where the total sales is greater than 1,000. So now we're only looking at big orders, and that then the data down by quite a lot. So those are the two parameters: SQL always where and SQL always having. Move on to the second filter parameter. This is how SQL always where and SQL always having would look in an Explorer, along with the resulting SQL. Because there are both parameters that start with SQL, they need to end in double semicolons. SQL always where will even affect field filter suggestions in addition to looks and dashboards. With that test user example I described, if someone wants to filter on the user's full name dimension, the ensuing drop-down menu would not suggest any names containing the word test. This can be overridden with a full suggestion parameter, though. Note, if your Explore filter uses a field from a different view other than the base view, that view will always be joined into every Explore query, even if the business user doesn't explicitly select or filter on any dimensions or measures from it. The join needs to be there for the filter condition to work. Now we're going to talk about the always filter. Always filter adds a filter to the Explorer front end. It has the word required under it, so although users can change the filter operator and values, they cannot remove the filter itself. Always filter has a subparameter of filters, which works exactly the same as the filtered measures using looker filter expressions. Because business users can see and modify the filter criteria for always filter, the use case for it is different from the use case for SQL always where and SQL always having. We are suggesting a default filter because it is probably what most people want, while acknowledging that there could be other possibilities. For example, most of the time we probably only want to analyze orders with the status of complete, but it is reasonable that sometimes we might want to look up in an order that is not yet complete. And maybe with most of our e-commerce company based in USA, most of the time we only want to analyze orders where the country is USA, but occasionally we might still want to look up orders in other countries. So let's apply the always filter and show you what it looks like. Send this to you. So in this always filter, we are filtering on status equals complete and country equals USA. So let's save and validate, and I'll show you what it looks like in the Explore dropdown. So what this does, as you can see, is it actually adds them as filters, and they're both required. You can't even get rid of them. So that's the use of the always filter. It gives the user, it applies the filters as filter dropdowns for the user to change if they want, but they are forced to have a value in it. And when it comes to how it gets applied in SQL, it just gets applied as a where statement. Lastly, we have the conditionality filter. Same as always filter, this adds a filter to the Explore front end. It has the words conditionally required under it, so although users can change the filter operator and values, they cannot remove the filter itself unless they put a filter on a specific alternative field. Conditionally filter has two subparameters. The first one is filters, which works exactly the same as in always filter, and filtered measures using Looker filter expressions. The second parameter is unless, which calls out the alternative fields a user could filter on to eliminate the default filter. The use case here is just to prevent users from creating and running very large queries. We're saying there isn't necessarily a salient business reason for this filter, but rather it uses a dimension that would be very helpful in cutting down the amount of data you query. Date and geographic fields tend to be good choices for conditionally filter. So this is the application of the conditionally filter applied to the Order Items Explorer. It's got the base filters of which it's going to explore the query by, and it's saying unless you use ID or state, that's the only scenario in which you can get rid of these two top filters. It's rather confusing, but if I show it, it will make better sense. So it's showing status equals complete. Why is it showing countries equals USA? So I can't get rid of this this filter right here, but if I were to go and enter in one of the unless parameters, ID or state, so if I go to users.id, I don't have ID, let's go to state. So if I put in state, now I actually can get rid of this filter. And so basically what this filter is used for is to just make sure that, like, if you got a billion row table that's very expensive to query, it's like it's a guardrail that prevents big queries from being ran just to save costs. It says, you're going to have to apply a filter unless you use a different filter. Then you can make changes, and it's all for the sake of just ensuring that no one's running super big queries. So let's give Explore filters a try. So the first question, the business user only cares to analyze large orders totaling 200 or more, comprised of 5 or more items that were not returned. So this is asking for both a SQL always where clause of it not being returned, and then a SQL always having clause where the total sales is greater than 100. That's these two parameters right here. You drop those in the Explorer, so we're only going to be looking at items that aren't returned with total sales over 200. So if I save and validate, let's refresh this. So like with the SQL always where and SQL always having, the only way you can see the application of those filters being applied is in the SQL statement. You see the where clause is where we're only going to be looking at items that weren't returned. And then there's a having clause that says the total sales has to be greater than 100. For the second question, users who actually have purchased items most of the time. So in this scenario, it's the same exact application of having a SQL always where clause and a SQL always having. We're only going to be look at where the status is complete and then the order count is greater than 5. And there you see the where clause from the SQL always where being applied, and then the having clause from the SQL always having clause being applied. The third one, the business only cares to analyze orders from the past 2 years, except when looking up a specific customer's order history. So that's calling for the conditionally filter, where we're only going to look at orders in the past 2 years, unless you're going to be looking up a full, a single user, then it's going to show the complete history for that user. Let me send that in the chat.
I think we got 2 of the same chat. I don't think it captured the copy paste on that one.
Oh, okay. Thank you. So because with the conditionally filter, it's only going to be showing data for the past 2 years. But if I go into the users and then filter on full name, now I have the ability to get rid of that. So let's find somebody. Now that I applied a full name value, I can get rid of the 2-year filter. Now I'm just showing a single user. It's filtering on Aaron Gates. The last one, we want to see new users on our platform most of the time. From my notes, this is the calling for the always filter. So in the always filter, we're only going to be looking at orders that took place before today. And I'll show you how that before today gets executed in SQL. So there we have our required filter for registrate is before today. And you see it's got some dynamic logic. It's got this get date value that's asking for the current date, but it's making sure that there aren't any orders that happened before today. So nothing today. Okay, we just finished day one. How about we take a 10-minute break, and we can come back at 11:05. Does that sound good?
Yeah.
Yep,
Alrighty.
thank you.
See everyone in 9 minutes.
Cool.
All right, let's get started. Can everyone see my screen?
Yep.
Awesome. Let's get started. Let's talk about caching. Caching is a useful feature that reduces database load and helps to optimize Looker performance. We use LookML objects called data groups to define caching policies. As you know, Looker is constantly generating SQL queries and sending them to the connected database. Caching uses saved queries from prior queries so that not every query needs to be run on the database repeatedly. This helps reduce database load. A data group is a Looker term for caching policy or rule. Whenever someone runs a query in Looker, the SQL and its results are stored in an encrypted file on the Looker instance. Looker acts like a bouncer for the database. Next time someone runs a query, it checks to see if the exact same query has been run before. If not, it allows the query to run on the database. When the results are returned, Looker caches them for future reference. If the same query has been run before, Looker checks the caching policy to evaluate whether the results should be considered valid or not. If yes, Looker returns the cached results to the end user. This happens in just about half a second. If the same query has run before, but the results are no longer valid per the caching policy, then Looker still sends the query to the database to get new results. It then caches the new results for future reference. We can use data groups with a few Looker objects. At the model level, we could be telling Looker that all explorers within this model should use the same caching rules. We could also apply a caching policy on an individual explorer, which would override whatever is set at the model level. And again, since explorers are the foundation of all content, the same caching logic would carry over to looks and dashboards. In a persistent derived table, which is a data structure customized in Looker and written back to the connected database, we will learn more about that in our later training. We can also use data groups for schedules for looks and dashboards, which can also be run on data groups. We can instruct Looker to run a look or dashboard automatically upon expiration of a caching policy, so new data is returned and pre-cached for any business user who needs it. To recap, data group is the Looker word for a caching policy. We can configure the caching rules for models, explorers, and PDTs. What kind of data group you want to create varies widely from customer to customer, even from team to team. It all depends on your data's ETL, processes, and business requirements. Data groups take two parameters, and only one is required, but it's best to have both so that one can act as a fail-safe for the other. In SQL Trigger, we need to write a SQL statement that will return only one value. Looker will take this statement and ping it to the connected database on a regular frequency. It basically keeps asking, what's the result? How about now? How about now? Did it change yet? And once it finds the result has changed, it takes that as a cue for it to invalidate the cache. In other words, next time someone tries to run the same explore query again, the query will be sent to the database to retrieve updated data. The frequency of the SQL trigger pinging is defined in the connection settings by the Looker admin. By default, it is every 5 minutes. However, if your data warehouse is only updating every few hours or once per day, every 5 minutes is a bit excessive. Also, customers on certain dialects such as Snowflake want to let their database hibernate outside of work hours to save money, so that they would not want Looker waking up with SQL trigger checks every 5 minutes. The frequency is determined by a cron string in the connections PDD and data group maintenance schedule field. If you expect your data to update only once per day at midnight, you could write a SQL trigger to say select current date. Since this is a parameter that starts with SQL, you may need to replace current date with the appropriate function for your dialect, such as getDate for Microsoft SQL Server. If you want Looker to refresh the cache whenever a new row is detected in the table, such as order items, your SQL trigger could be select count star from the base table order items. The other parameter is max cache age, which specifies the number of hours to keep a cached result. Some people use max cache age by itself and say, no matter what's going on with my data source, any query should only be cached for 1 hour. Or again, as a better practice, they use both parameters together and say, even if no change is detected by the SQL trigger check, that could mean something went wrong with the ETL or SQL trigger itself. So let's refresh the cache regardless after, say, 6 hours. So let me show you what this looks like. So the cache is defined in a data group. It has two parameters. Only one has to be used, but it's okay if both are used. Both could be used as a failsafe. Do that right here. The SQL trigger only returns a one cell value, so it's, you got to understand what kind of SQL you can write. It only can return one row and one column. So, for example, max ID. So if the ID just goes up and up and up as new data comes in, this trigger would detect when new rows come into the data, invalidating the cache and telling the database to give us a new query. And then the max cache age says that no cache can be older than 24 hours. So it knows how old each cache is. If it's older than a day, then regenerate the results. And then to persist the data group, you just use the persist with function that calls what the data group name is. Now, since this is happening in the model file, and we're not applying this to an Explorer, but we're applying it to the model, this cache is going to be effective for every Explorer in this model. Right now in this model file, we have two Explorers. We have order items and users. So this cache is going to work for both Explorers. Let me give that to you in the notes. And yeah, this unfortunately isn't something we can, test. But, I said yesterday that Looker's really great because there is no data movement. This is like the one instance of when Looker actually ETLs data into its own environment. But you could be rest assured that this data is extremely well encrypted, and it's not going anywhere, and it's safe. Configuring a data group by itself doesn't do anything. It's a two-step process. Next, we need to apply the data group somewhere using the parameter persist with. As mentioned previously, data groups can be applied at the model or explore level. If we persist with a data group in the model file, all the explorers in the model will use it. If we persist with a data group within the definition of an explorer, then that overrides any data group already being used by the model. We can also persist with the same data group within the definitions of multiple explorers, which would also override any data group already being applied at the model level. We also said earlier that data groups could be used to persist derived tables, and that is our next topic. But now we got an exercise to do. So the question is, data engineers say we only sync user data between our transactional and analytic databases every 24 hours at night, while executives say we need to see real-time order data or as soon as it is available. So for the first one, we're going to make a data group that's going to define the caching policy. And we want this to refresh every 24 hours. So the max cache age is 24 hours. And the cache is also going to refresh as soon as midnight takes place and it's a new day. Let me give you that file. So you define the data group always at the model level, but you have the ability to persist it within the model file right here. So this is at the model level. But for this one that we're doing right now, we want to persist it only to an explorer. So the persist with parameter is within the order items explorer. Let me give you that. Are we having, I'm looking at the notes right now. Are we having trouble rejoining?
Yeah, I think there's a team member that's having trouble joining the meeting.
Okay. Well, we'll continue on. They can see the recording. They need it. So once again, we can't test, the validity of this working, but just so you know, data groups are applied, or caching is defined using a data group. You use two parameters. You can either use one or the other, but it's okay to use both. And then you can apply it either at the model level or at the explore level. Yeah, my apologies. This data group I applied to the bottom explorer, the users explorer. And then for the second question, this data group, which I called order items, which refreshes every 4 hours, or when the created date changes to a new day, that's applied at the order items level. So far we've dropped the term derived table a couple times, and now we're finally learning about them in earnest. So far, we've been working with tables that already exist in our connected database, such as users and order items. We've seen the table names in the SQL table name parameter for our views and in the SQL generated for our Explore queries. However, it is not unusual for existing database tables to be insufficient. Sometimes we need to structure our data in other ways through SQL objects like temporary tables, materialized views, common table expressions, and subqueries. The most common use case by far is to overcome structural limitations for patterns that would require a subquery and raw data. That is, we need to do things that are not possible with the basic way that Looker generates SQL through LookML dimensions, measures, views, and explores. Nested aggregates is a common pattern where we need to do an aggregate of an aggregate. Consider the example of trying to find which department has the highest total sales. This first query won't work for two reasons. We cannot take the max of a sum. Any database dialect would complain about these nested aggregates. The other is that group by logic needs to be applied separately. So to resolve this issue, we would isolate the first aggregation and grouping into a subquery, and then we find the max of those subquery results. Here is another example. How many of you shop at Amazon? How many years have you been an Amazon customer? And throughout those years, how much money would you say you've spent on Amazon in total? Businesses are very interested in analyzing this sort of thing, customer lifetime spend. They also want to know what's the average customer lifetime spend, say for people aged 25 to 35, or for people in the state of New York. In the Explorer, we can easily grab the user ID dimension and total sales measure to find each customer's lifetime spend. But how would you get the average of this total? How would we find an aggregate of an aggregate? If you're really clever, you might figure you can divide the total sales by the count of users, and that should give us the average customer lifetime spend. How about something else though? The average number of days elapsed between a customer's first and second orders on our e-commerce platform. In SQL terms, what we need is a CTE, or temporary table. We need to transform or flatten the total sales measure into a dimension so it becomes just another quality or attribute for each user. Then, since it is a dimension, we can perform an aggregation on it without creating problems with nested aggregates. We can successfully calculate the average customer lifetime value. In Looker terms, if you need to produce a CTE or temp table, you need to define a derived table. Here's another scenario. The order items table we've been using in this training can have many items per order, like a shopping cart. We want to do some shopping cart analysis, like are there any patterns to or drivers behind orders that contain multiple items as opposed to just one? How can we filter out the orders with one item and look at the ones with multiple items? Another question. What is the average number of items people tend to combine in a single order? This would be like an average of a count. How can we classify high versus low value orders? This would be like doing a case win for each order ID sum of sale price. Another one is, what is the average total cost, given that our tables is granular at the item level? Another question about the average of a sum, like the question of average customer lifetime spent. So I hope you guys, through these examples, you guys are understanding, like, these are questions that can't be answered just in a general SQL query. You need to aggregate twice. You need to build an intermediate subquery and then do some analytics on the aggregated table. This is a very hard concept in most data visualization tools, and I think Looker handles this the best, giving you the ability to build derived tables It's a very powerful, tool that you have in your toolbox in order to derive any metric or dimension that you need in your data. So to the left is a structure of the data we actually have in our table. To the right is the sort of order fact structure we need to answer those questions with. We need each order ID's count of items and the sum of sale price to be a dimension of or a fact in the order. So in our order items table, the data is unique by order ID and item ID. And we want to look at just information at the order ID level. There is no table in our database that is unique by order ID. So we're going to make one using a derived table. And that's going to allow us to do some calculations on the metrics from that subquery as if they are dimensions rather than measures, so that we can do the aggregate of an aggregate with no problems. Derived tables enable us to create the necessary structures to address all kinds of data questions. Often, the way the data is stored in the database does not meet or align with business requirements. We've already walked through a couple of use cases where we would need to pre-aggregate or dimensionalize metrics. Some more situations where we would need derived tables would be raw event data needs to be partitioned or organized into user sessions based on specific activity timeframes so we can analyze behavioral patterns. Another example, order information needs to be rolled up by customer and month so we can determine things like average amount of time that passes between one order and the next. Lastly, data from the tables for various marketing channels such as Google, Facebook, and Twitter need to be unioned together in one big table so we can calculate and compare KPIs across all the channels in one place. So with that fourth example, we're talking about a union between tables. The only way that you can actually perform a union in Looker is through a derived table. Using derived tables, you can write any SQL query you want. Derived tables are manually written or produced select statements where the result set can be queried just like a real database table. They are integrated in LookML projects as views. We can explore and join those views, same as views pointing to real database tables. Derived tables have two types of existence. Ephemeral ones compile at runtime and are generated as CTEs or temp tables. The other option is persistent ones, or PDTs, which run a create table statement on the underlying database and are stored there as long as you want. The benefit in persisting derived tables is that they are ready to go when business users need them, and therefore reduce query runtimes. The downsides are that they take up storage space in your database, which may correlate to cost, and they are more rigid. They can't accept dynamic logic or take advanced. If you want to learn more about this, you can take the Advanced Developer Bootcamp, which we are planning to do in a few weeks. So this is a really cool example about Looker. It has the ability to write to your database. With persistent derived tables, you can create tables inside your database, and this is very important for when you're working with very large tables and you want the user experience to be quick as they're navigating through the dashboard. It is sometimes better to persist derived tables rather than making them ephemeral, which means that they're going to be derived on the fly every time they are used. There are two types of derived tables, SQL derived tables and native derived tables. So independent from the two types of existence that we just said in the previous slide, ephemeral versus persistent, there are now actually two methods for writing or describing derived tables. The first way is through SQL, this tends to be pretty easy to learn and understand when you're already comfortable with select statements. SQL derived tables have the advantage of being able to leverage complex or custom joins and calculations and the union function. Derived tables can also be written in LookML, which we call native derived tables. This adheres to LookML's core tenet of code reusability by allowing you to inherit existing objects and definitions from your model. They are much easier to maintain, allowing your model to scale better as your organization's usage of Looker increases. Although they can be intimidating at first, once you get more accustomed to LookML, you will also find NDTs easier to read and understand. I'm sure many of you knew SQL before you knew LookML. And in the heat of battle, many of you would rather save time and write SQL-derived tables instead of learning an alternative approach, which would likely save you more time further down the road. So let's tackle SQL-derived tables first. The easiest way to create a SQL-derived table is through SQL Runner. In the IDE, you can click on the plus sign icon in the file browser and create a view to write your whole derived table from scratch. But it would be a lot more work because you can also write all your dimensions manually too. So once you've, let me just show it to you in So SQL Runner is a very powerful tool. When you're in SQL Runner, which you just go to develop SQL Runner, you have the ability to connect to any connection that you've defined in your Looker instance. So if we go to the e-commerce connection, now we're looking at the raw data coming from our project. I paste the SQL query in. What I'm doing is I am aggregating the data by order ID, and I'm getting some summary statistics at the order ID level. Let me paste this to you. So there's our table. There's our, the results of our query. Now, the next step to creating a derived table would be going to this gear option. And you have the option to either add to project or get derived table, LookML. That actually gets you to the same destination, but this one is in 2 steps in that you can just add it to project right here. This takes you to the same place as it before, but this is converting your raw SQL query that you see right here into a derived table, and it's got all the LookML defined for it already. So we can add it to our project, and once you do that, make sure we are selecting the right project, and that's at the bottom. It's Data Analyst Bootcamp, and then we can give this view a name. Let me call it order level info. So I can add it to the project. And now you see this order level info is treated as its own view. If I go into it, it's telling me it's a derived table. This is the SQL of the intermediate table, and then it's got all the dimensions defined. Let me validate this. Another thing to keep in mind, just for when you're developing in Looker, this tab was originally SQL Runner, but then I added the SQL to a project, and then now I'm in my my LookML environment, which is the same environment as this. I just want to hammer the point: you never want to have the two browsers open that have the same the same portion, part of Looker. Right now I got the LookML shown in two browsers, and that's just rather dangerous. So let's change that to SQL Runner. And then if I just refresh this, let me save and validate. If I refresh this, there's the order item derived table that we viewed. For aesthetic purposes, you're going to want to drop it into the views folder. Not necessary, but just to keep it clean. And then there's some cleanup you want to do with this table. The first one that you always need to do is define the primary key, which is order key. And let's add a few dimensions that you couldn't do without the use of a derived table. Let me give you the first one. So the first one is a flag, a yes/no flag, and it's just going to determine whether multiple items were purchased on the order. Is it a multi-item order or not? The second one is very similar. I just want to determine whether the order was a large order or not, whether the order total was greater than 200. So these are things that you can't do without derived tables. If you think about how you would do this, how would you create a flag that determines whether it's a multi-item order or not? You're going to struggle trying to figure out how to do that, and you can't, just because it's you need a pre-aggregated table in order to make that logic work. So we defined two new dimensions, and we got our order level info table, but we haven't yet joined it to our base table, and that's what we got to do next. So now that we've done everything we wanted into the view file, we got to go into the model file and join it, and we'll join it to our order items table. So we can just go to the bottom here, type in join, and this is the view name, so order level info is what I call it. The type, is the left outer. SQL on is order items, order IDs. So that's coming from the base table, and then order level info, order ID. So you can let Looker finish when you're entering a column name. It's always best to let Looker finish it for you. The last parameter that we need to put in, relationship equals many to one. So now if we save changes and validate, and refresh, now we got our derived table in our Explorer, and that gives us the ability to filter on these values, or use them as dimensions, whatever you want, just like any other dimension in the data model. So there we go. We have a yes no flag that determines whether there was multiple orders on the order or not, whether there are multiple items or not. Now, if we go to the SQL, this is very interesting. This with statement tells you that this is a CTE, or a temporary table that's being first derived. So basically, Looker is telling the database, step one is to define this subquery. This is the derived table that we just defined, exactly as it is, the exact same logic. Once you define that, now let's use that derived table. Let's join that derived table that we just defined here into the base table and use its metrics like we do. This is just like any other SQL that we saw earlier, and it's joining in the derived table, which gets defined right above using the with statement. So like I said, just to summarize what I just did, and it's kind of rather complicated. You get the hang of it. Step one is to define your query in SQL Runner. You don't necessarily have to define it in SQL Runner. Let me show you another trick that we could do. So I'm in an Explorer, and let's say I want to make that same order level table. Or we'll just order items, count, total sales, total profit. So in our example before, I just dropped the SQL statement in for you, assuming that I wrote this by hand, which is very possible, but an even quicker way to derive this table is to just build it in an Explorer like I did right here. And if I go to SQL, I have the option to open in SQL Runner. So that essentially gets me exactly where I was right here. The only difference is I changed the field name, so this would just be order ID. And then everything else is the same thereafter when it comes to building out the derived table. But it's very valuable. You don't need to necessarily write SQL by hand in SQL Runner. You can build your view in an Explorer and then export the SQL Runner code to SQL Runner, and that will get you there too. So yeah, step one, write your query in SQL Runner. Step two is you hit this gear and then you add it to project, or you can just get the derived table lookml. This function right here. You can add either one of these two would work. Step three is defining the project that you want to put it in, and then you give that derived table a name. Step four is, you're in the lookml IDE. The derived table is created. You want to do some cleanup like primary key and then add any new fields that you want. And then the last part that we didn't mention is just making sure you're joining it back to your root table. So going into the Explorer and then making sure you join it back to your root table so that you can use it. And here's an acronym that Google created. Free lunches cause positive moods. 5 steps after creating a shiny new derived table. Step 1, F for folder. That tells you to move the view file to the appropriate folder. Step 2, L for limit, is to erase any limit in the SQL. The limit function, if you want to, most queries have a default limit of 500, but when it comes to any derived table, you never want to have a limit function. You want to get all the data. Step 3 is C for causes. Remove or hide any count measures. We didn't talk about that, and I don't find that totally necessary. Step 5 is P for primary key. Establish the primary key. And M is for measures. Write the desired measures of any additional dimensions. It is 11:50, I think. That's all we have for today. Yep. So that means we can call it a day, and we will get right back on track tomorrow. Thank you for attending the second day of our session.
Thank you.
Thanks.
Thanks, Danny. Much appreciated.
You're welcome.
See you all tomorrow.
Thank you. Great work, Danny.
Thanks, Jake.